Have you ever stopped to wonder how a self-driving car spots a stop sign? Or how an app on your phone can scan a document and turn it into text? It all starts with something really fundamental, teaching a computer how to tell an object apart from its background. So today, let's break down one of the most foundational concepts in all of computer vision. So to really get how those incredible technologies work, we've got to start at the beginning. We need to understand the basic problem a computer faces when it just tries to, well, see the world like we do. Let's frame this with a simple question. Picture a robot playing a cards game. How in the world does it actually know what cards it's holding? For us, it's instant. But for a machine, that's a huge challenge. See, when a computer looks at this picture, it doesn't see a hand of cards. Not at all. It sees a giant grid of pixels, and each of those pixels just has a brightness value. It's a mess of numbers. So before that robot can even think about what to play, it has to simplify all that data down to what actually matters, the symbols on the cards. And that brings us to the first and probably the most important tool in the entire computer vision toolkit. The technique is called image thresholding. And honestly, you can think of it like a simple light switch for every single pixel in the image. We just pick a certain level of brightness, that's our threshold, and if a pixel is brighter than that, we flick its switch on, turning it pure white. If it's darker, we flick it off, making it pure black. The rule itself couldn't be simpler. We just pick a value, let's call it T. For every single pixel, we ask, is your brightness higher than T? If yes, you become white. If no, you become black. That's it. We're literally forcing every shade of gray to pick a side. And when it works, wow, the result is incredible. On the left, you see the original image with all its subtle shadows and textures. And on the right, the thresholded image. All that noise is just gone, leaving behind these crisp, clean symbols that a computer can easily recognize. Problem solved, right? Well, not so fast. Because as powerful as this simple idea is, it has one major weakness. And it's that picking the right value for T is everything. Just look at what happens when we get it wrong. If we set that threshold too low, parts of our symbols just vanish into the white background. But if we set it too high, we start picking up all this junk, shadows, parts of the card itself, all sorts of noise that makes the final image completely useless. Which really begs the question, right? What makes finding that one perfect number so hard in the real world? And the answer, the main villain in our little story today, is something we deal with all the time. Bad lighting. Shadows, bright spots, gradients, they completely destroy our simple little model. Okay, so here's the core problem. In a perfect world, all the pixels that make up the spade symbols are darker than all the pixels that make up the white card background. Easy. But in reality, a shadow on the white part of the card can easily become darker than a brightly lit part of the black spade symbol. The lines between object and background get totally blurred. Now, there's a really cool way to visualize this. It's called a histogram. It just counts up how many pixels there are at each brightness level. In a perfect world, you get this beautiful chart with two distinct mountains. One mountain is all the dark object pixels, the other is all the bright background pixels. And picking our threshold T, it's as easy as finding the nice, clear valley right between them. But now look what happens when we have uneven lighting. That beautiful, clean separation just completely disappears. The two mountains basically collapse into one big, messy, jumbled up hill. There's no obvious valley anymore. There's no single right place to put our threshold T. Any number we pick is going to be wrong for some part of the image. So if we can't just look at it and pick the right number, is there a smarter, more automatic way to find the best possible single threshold? Oh yeah, there is. It's a pretty clever algorithm that basically hunts for that valley for us. Here's how it works. First, you just make a rough guess for T. Then you split all the pixels into two teams, a dark team and a bright team. You figure out the average brightness of each team, and your new, better guess for T is just the average of those two averages. You just keep repeating that process over and over until T stops changing. And for images that have that nice two-mountain histogram we talked about, like this fingerprint, this algorithm is fantastic. It automatically finds that perfect sweet spot to separate the dark ridges from the light background. But what about our original, messy problem? Even this smart algorithm can't solve the main problem of uneven lighting with just one single number. This is where this global approach fails, and we need a way to, well, adapt. And here it is,
our difficult image, processed with the absolute best single threshold that algorithm could find. And as you can see, it's a complete failure. The left side is crushed to black, the right side is blown out to white. We've lost everything, because one threshold just can't handle a shadow on one side and a bright light on the other at the same time.
And this brings us to the hero of our story, adaptive thresholding. The logic here is just brilliant. If one threshold doesn't work for the whole image, why not just break the image up into a bunch of smaller pieces and find a separate, unique threshold for each tiny piece? It's a classic divide and conquer strategy. And this visualizes the idea perfectly. By laying a grid over the image, the algorithm can look at each little square one by one. The squares on the left are in a shadow, so they get a threshold that's right for dark conditions. The squares on the right are brightly lit, so they get a completely different, higher threshold. It adapts to the lighting in each little neighborhood, solving one big impossible problem by turning it into lots of small, easy ones. All right, so let's just pull back for a second and look at the journey we've just been on. We started with what seemed like a simple problem, and we've ended up with a really elegant and powerful solution. So what are the key takeaways here? First, thresholding is this core idea of simplifying images down to just black and white. Second, using one single or global threshold for the whole image works great, but only in perfect lighting. Third, the real-world villain is always uneven illumination, which just messes up our data. And finally, the really powerful solution is adaptive thresholding, which wins by thinking locally instead of globally. And that leaves us with one final thought. We've just walked through all of this complexity, all of these challenges and clever solutions, just to get a computer to see the difference between black and white. So if this is what it takes for step one, just imagine the incredible, mind-boggling challenges that have to be solved for a machine to truly see and understand our world in full, vibrant color.